Welcome. Let's take a look at evaluating the integral of x squared times the square root of x plus 1 on the interval from 0 to 3. Notice that this is not a basic integrand. In other words, I cannot look at it and know what its antiderivative is, so I'm going to try to use some substitution. Typically, when we try to use substitution, we look for elements of the integrand that are components or of the derivative of another element. So, for example, if I let u equal x squared, then du would be 2x dx. And if I had an extra x floating around, I could substitute. And so I could say, okay, well, this part I'll make a u, but if I call u x squared, I'm a little bit stuck at what to do with the x plus 1. Now, we never want u to equal x, because then du equals dx, and basically we have the same integral that we started with. So that's not helpful. This is not helpful because while I have this x here, it's stuck underneath a square root. So that's not particularly helpful. So what have we considered? Well, we considered I could take this, but that was this guy, and that wasn't helpful because x is stuck underneath a square root. We thought about possibly just taking this x, but if I just take x as my substitution, I'm just recreating the same integral that I started with, so that's not helpful. So we tried this, we tried this. What else can we try? Well, what else we can try is, what if we let u equal x plus 1? So what if we let all of this under here equal u? Well, then you might be wondering, well, okay, fine, but what about the x squared? Well, let's see. If u is equal to x plus 1, what does that mean about x squared? What does that mean about x squared? Well, if u is equal to x plus 1, then u minus 1 is equal to x. And if u minus 1 is equal to x, then I can use this information, and my x squared can become u minus 1 squared. And you're probably thinking, okay, but how does that actually play out? Well, okay, so let's take a look. So if I do that, then my x squared becomes a u minus 1 squared. Now remember, I just grabbed this piece underneath the square root, right? This x plus 1 is all that's the u. So we're going to have u to the 1/2 power. I'm going to go ahead and write the square root as an exponent. So all of that looks pretty good, actually. I've replaced the x squared. I've replaced the square root of x plus 1. I still need to deal with the dx. So let's come back over here. If u is equal to x plus 1, then du is equal to the derivative of u. The derivative of u is 1 dx. Or we could just say that du is equal to dx. So I can replace my dx with du. And now I've replaced the integrand. I've replaced the differential. All that's left to replace are my limits of integration. Let's see how that plays out. If x is equal to 3, then u is equal to x plus 1, so that would be 4. If x is equal to 0, then u is equal to 0 plus 1, that's 1. So, for my lower limit, that used to be 0, and now it's 1. For my upper limit, that used to be 3, and now it's 4. And so I have a new integral entirely in terms of the variable u that we can start looking at evaluating. Now, the first thing I notice about my new integral is I have this u minus 1 squared. So we're going to need to expand or multiply that out. So that's going to become the integral from 1 to 4. Now keep in mind that u minus 1 squared is u minus 1 times u minus 1. So that's u squared minus 2u plus 1. So we're going to have u squared minus 2u plus 1 times u to the 1/2 du. Now, this whole thing is my integrand, so I'm not quite done with the algebra. I still need to continue to simplify this, multiply it out. So this is going to become the integral from 1 to 4 of u to the 2. Now, using rules for exponents, when I multiply those, I need to add the 2 and the 1/2. When I add 2 and 1/2, I get 5/2. Minus 2 times, now my exponent for u is 1 plus 1/2, so that's 3/2. And then plus u to the 1/2 du. Now, this is in a sum, and we have a bunch of powers, exponents to a variable u. These exponents are constant. We can use the general power rule to help us find that antiderivative. So, I have u to the 5/2, so my antiderivative is going to be u to the 5/2 plus 1. 5/2 plus 1 is 7/2. And so I'm going to multiply by 2/7 for my antiderivative minus 2 times u to the 3/2. Antiderivative, I'm going to add 1 to that exponent. So 3/2 plus 1 is 5/2. So u to the 5/2. And then for my antiderivative there, I need to multiply by 2/5 plus u to the 1/2. I need to add 1 to that exponent for the antiderivative. 1/2 plus 1 is u to the 3/2. And then for my antiderivative, I need to multiply by 2/3. And then we're going to evaluate that between u equals 1 and u equals 4. So bringing that up over here, we have 2/7 times 4 to the 7/2 minus 4/5 4 to the 5/2 plus 2/3 4 to the 3/2 minus, now substituting in the 1, our lower limit, 2/7 times 1 to the 7/2 minus 4/5 times 1 to the 5/2 plus 2/3 times 1 to the 3/2. Now, I'm going to use a property of exponents to help me finish simplifying that. And let me remind you of that property. That property says that a to the m over n power, so a fractional exponent, can be thought of as the nth root of a raised to the m power. So as I go through this, we're going to have 2/7. The square root of 4 is 2, and so we're going to have 2 to the 7th power minus 4/5. Again, the square root of 4 is 2, so 2 to the 5th power plus 2/3. Now the square root of 4 is 2, so we'll have 2 to the 3rd power minus, and then these are all powers of 1. So this is 2/7 minus 4/5 plus 2/3. Now notice that all of my denominators are prime. So if I were searching for a common denominator, its factors would be 3 times 5 times 7. So for example, in this first term, if I needed a common denominator, I would need to multiply by 3 times 5 over 3 times 5. And so my common denominator would end up being 3 times 5 times 7. For my second term here, I would need to multiply by 3 times 7 over 3 times 7. And for my third term here, I would need to multiply by 5 times 7 in both the numerator and the denominator. And doing similar over here in my second set of parentheses, my second group, I would multiply by 3 times 5 over 3 times 5. This would be 3 times 7 over 3 times 7. And lastly, this would be 5 times 7 over 5 times 7. So it turns out this common denominator is 105. So we're going to have something over 105 minus something over 105 plus something over 105. And then we'll need to distribute this minus sign. So minus something over 105 plus something over 105 minus something over 105. So now we need to figure out what these numerators are, right? All right, so starting with our first numerator, we have 3 times 5 times 2. That's 7 plus one more factor of 2, so 2 to the 8th. So this is going to be 3,840 105ths. Our next numerator is 3 times 7 times 2 to the 5th. And that, and times my 4. I can't forget that 4 times 4. And that's going to be 2,688. My next numerator is 5 times 7 times 2 times 2 to the 3rd, which is 560. Continuing on, 2 times 3 times 5, that's going to give us a 30. 4 times 3 times 7 is going to give us an 84. And then 2 times 5 times 7 is going to give us a 70. And so to get our final answer, we're just going to combine all of those numerators through addition and subtraction. And when we do that, we end up with 1,696 105ths. I hope you find this helpful.